Likewise, as Copernicus presented the heliocentric model, we could notice one more eminent correction in our tremendous understanding. A conversation in cosmology known as the emergency of cosmology has emerged. Neil deGrasse Tyson asserts that the James Webb finding has settled this conversation with a physics-breaking picture. So, what is this crisis, and how has the James Webb Space Telescope added to it? For those new, it's difficult for old folks to check it as a crisis. However, we view ourselves as in a situation where we didn't absolutely know the age or size of the universe, as they are connected within a variable of 2. Join us as we explore the actual outskirts of science, where our information is constantly questioned and unforeseen disclosures are made. The Standard Model of Cosmology, a critical achievement throughout the past 100 years, structures the universe's arrangement of encounters and present status. Gravity, mediated by general relativity, essentially directs the universe's advancement, sorting out its expansion and the arrangement of huge vast designs. Parts incorporate dark energy, dark matter, ordinary matter, neutrinos, and photons. The universe began from the hot enormous detonation around 13.8 quite a while back, preceded by expansion causing density imperfections. However, this model, not enduring expansive observational support, is currently under an amplifying glass with the JWST. Cosmologists have a new tool that has been making issues in our norm model. In the early universe, before stars or systems emerged, unbiased molecules formed around 300,000 years post-Big Bang. Reionization happened 550 million years at some point sometime later when the majority of the universe became ionized. The JWST permits cosmologists to uncover more distant worlds than previously conceivable, offering new insights into the early universe. The Standard Model, known as the inflationary hot enormous detonation or lambda CDM, has sorted out different elements of the universe, actually. However, conflicting proof has emerged, resulting in an emergency of cosmology. The emergency is critical. We don't extraordinarily know the age of the universe, and different methods give different results. One technique used to measure the universe's age is the vast microwave foundation. Scientists dive into the universe's expansion history using mathematical modeling based on Einstein's general relativity hypothesis. This hypothesis generates the Friedman conditions, connecting the universe's structure with its expansion rate at specific times. The cosmic microwave background, staying light from the early day of the universe, is a significant apparatus in measuring its properties. However, exact maps of the CMB like those from the European Space Agency's Planck mission need data on dark energy, a critical player in the ongoing universe. Despite these challenges, scientists use the Friedman conditions to determine the growth rate of the universe at any given time. They can determine the universe's growth rate and, subsequently, its current age. Another method to measure the universe's age is by investigating exploding stars. While the vast microwave background provides a detailed record of the universe's creation, it's essentially a historical portrayal, beginning billions of years ago. Noticing the universe's growth rate directly is conceivable through abnormalities like type Ia supernovae, where a star dumps its air onto a nearby white dwarf, leading to a stunning blast. These supernovae act as reliable benchmarks, known as standard candles, allowing scientists to estimate the universe's expansion rate at the time of their event. This method, urgently used in the late 1990s, played a significant role in finding dark energy, becoming a cornerstone in cosmological measurements. It's particularly useful for determining the Hubble constant, a measure of the universe's expansion rate since the Big Bang. However, recent observations have shown errors in the growth rate, indicating likely unknown forces at play. NASA has noted a charming observation. Assuming that the universe's expansion slows, it suggests a possible influence of unknown forces like dark matter. On the other hand, if the growth rate accelerates, it may be attributed to dark energy. The Hubble Space Telescope and other instruments have measured changing growth rates across various observation points. Edwin Hubble, after whom the telescope degree is named, first proposed the expansion rate in 1929. Initially interpreted as galaxies moving away from one another, it's now recognized as the universe's expansion. However, reconciling measurements from different telescopes and methods remains challenging. Despite technological advancements, errors persist in measuring the universe's age and growth rate. While these advancements aim to answer critical questions, they often raise more uncertainties. One proposed explanation for the mistakes involves likely flaws in cosmic microwave background measurements or variations in dark energy over time. Another possibility is the complexity of modeling supernovae accurately, leading to uncertainties in their use as cosmological tools. The James Webb Space Telescope, while adding to our understanding, has also complicated cosmological issues, further suggesting the need for a reassessment of our current scientific understanding. The Flamingo Project, a critical drive within the Virgo Consortium, addresses a multidisciplinary effort, including astrophysicists, cosmologists, computational scientists, and data analysts. This collaborative effort is focused on conducting extensive computer simulations that span the entire cosmic timeline from the early moments of the universe's origin to the present day. These simulations are powered by sophisticated algorithms and numerical techniques that embody our current understanding of fundamental physical processes governing the universe. By comparing these simulations against a wealth of observational data, scientists can validate their models and gain further insights into the underlying mechanisms driving cosmic development. This ambitious project requires significant computational resources, and the Flamingo Project uses high-performance computing clusters and supercomputers to carry out its simulations. These computational facilities enable researchers to simulate vast volumes of space at high resolution, allowing them to focus on the formation of galaxies, galaxy clusters, and large-scale cosmic structures with exceptional detail. Funding for the Flamingo Project comes from various sources, including grants from the European Research Council, national science and technology agencies, and scientific research foundations. This financial support enables the project team to access state-of-the-art computational infrastructure, highly skilled personnel, and faster global collaboration necessary for advancing understanding through the Flamingo Project and similar initiatives. By combining theoretical modeling with observational data, scientists aim to unravel the complexities of the universe's history and shed light on its fundamental properties. The Flamingo Project, a significant effort within the Virgo Consortium, embodies a collaborative effort among astrophysicists, cosmologists, computational scientists, and data analysts. This interdisciplinary approach is essential for tackling the complex challenges inherent in understanding the evolution of the universe at its core. The Flamingo Project uses advanced computational techniques to simulate the entire cosmic timeline from the earliest moments after the Big Bang to the present day. These simulations are powered by sophisticated algorithms that incorporate our current understanding of fundamental physical processes governing the universe. By comparing the simulated data to observational data, scientists can assess the accuracy of their models and gain insights into the underlying mechanisms driving cosmic development. The standard cosmological model recognizes any variations that may challenge our ongoing understanding of endless progression. Professor Carlos Hest, a critical collaborator in the Flamingo investigation and Ogden Professor of Key Physical Science at Durham School, stresses the significant moment in cosmology that the endeavor addresses. He notes that cosmology is at an intersection with new telescopes providing increasingly precise data that may not perfectly align with our theoretical models. This discrepancy raises questions about the validity of our current models and the probable presence of predispositions by the way we could decipher the universe. The Flamingo Project collects upon past reproductions that essentially zeroed in on cool dark matter but presently puts greater emphasis on incorporating ordinary matter, which contains just 16% of the universe, as well as neutrinos. Led by Professor Delicious Cupin from Hefty School, experts conducted extensive simulations using the COSMA 8 supercomputer, part of the Durham High Performance Computing Office. These simulations spanned over 2 years and considered the impact of both dark matter and ordinary matter, with a specific focus on the CHAP. To achieve these simulations, researchers presented a new code called FAST, which enabled the dissemination of computational tasks across thousands of central processing units, sometimes reaching up to 65,000 CPUs. This cutting-edge computational approach allowed for a detailed examination of the universe's progression, providing insights into the role of ordinary matter in shaping limitless designs. Despite the challenges presented by errors between observational data and theoretical models, The Flamingo Project addresses a concerted effort to push the limitations of how we could interpret the universe through rigorous computational simulations, interdisciplinary collaboration, and a commitment to scientific inquiry. Experts aim to unravel the mysteries of endless development and gain further insights into the fundamental nature of the universe. Albert Einstein's theory of general relativity reformed our understanding of gravity by conceptualizing existence as a unified fabric, which he named spacetime. This innovative framework described gravity not as a force acting at a distance, but rather as the curvature of spacetime caused by the presence of mass and energy. One of the significant ramifications of general relativity is gravitational lensing, where the shape of spacetime twists the path of light rays, leading to visible bends in the images of distant celestial objects. Gravitational lensing has become a significant tool in modern cosmology, allowing astronomers to study the distribution of matter in the universe and test its fundamental structure by examining the subtle distortions in the shapes and positions of galaxies. Researchers can infer the distribution of dark matter, which outweighs visible matter by a significant margin and exerts a gravitational influence on the light passing through it. Weak gravitational lensing surveys, in particular, have emerged as robust tests of cosmological structure. These surveys involve a statistical analysis of thousands of galaxies to detect the subtle gravitational distortions caused by intervening matter along the line of sight. By measuring the statistical properties of these distortions, astronomers can constrain cosmological parameters, such as the amplitude of density fluctuations and the matter density of the universe. However, recent observations have revealed a complex inconsistency between measurements of the universe's homogeneity obtained from weak gravitational lensing surveys and those obtained from cosmic microwave background (CMB) tests. The CMB, which is the residual radiation from the early universe, provides a snapshot of the universe's density fluctuations at a time when it was only 380,000 years old. Analysis of the CMB has yielded precise measurements of cosmological parameters, including the amplitude of density fluctuations, which are essential for determining the large-scale structure of the universe. The inconsistency, known as the S8 tension, refers to the difference between the values of the S8 parameter obtained from weak gravitational lensing surveys and those inferred from CMB measurements. The S8 parameter measures the level of matter clustering on large scales and is crucial for testing cosmological models. The tension arises because weak gravitational lensing surveys suggest a lower value of S8 than that predicted by the standard cosmological model based on CMB data. Efforts to reconcile the S8 tension have led scientists to explore various hypotheses ranging from possible systematic errors in the data to fundamental modifications of our understanding of gravity. Computer simulations, such as the Flamingo Project, have played a fundamental role in this endeavor by providing insights into the complex interplay between dark matter, ordinary matter, and gravitational forces in shaping the cosmic web. Despite the challenges presented by the S8 tension, several measurements taken between low redshifts and the CMB remain consistent with the standard cosmological model. This has led to the intriguing possibility that the universe may have undergone a gradual change in its evolution, testing our current understanding of cosmic structure and development. In summary, the S8 tension represents a significant challenge to how we could interpret cosmological structure and may require updates to existing theoretical frameworks. While it is unclear whether these discoveries will require minor adjustments or a complete overhaul of the book on cosmology, they highlight the dynamic and evolving nature of scientific inquiry and the ongoing quest to unravel the mysteries of the universe.